Hello, I'm Roman. Welcome back to a series of the videos of building the convolutional neural networks from scratch in Golang. In the previous video, I started to implement the MaxPooling layer and I finished with some parts of the convolutional layer. So today the goal is to continue doing the same. And I stopped on building the forward method for the MaxPooling layer. So right now, what we actually need to do is we need to implement this part of the code. So basically, the MaxPooling, what it does, it's, I would say, which one is better? I think. Basically, it reduces the, right? Yeah, so the MaxPooling takes the high value from the area covered by the kernel. So for example, if we have the MaxPooling of size 2 by 2, it means that we'll have to pick up a maximum value from the 4 items. So then the size will shrink by the pool size. Okay, what I did in the previous. Okay, so I just need some time to get back to what. Okay, so this one is actually taking current convention between the MaxPooling and the convolution layer that in the output I will have one row that will contain all outputs of the convolution operations. For example, if I had in the convolution 3 kernels, then I will have in one row first input size, which is the size of the okay, and we will follow the same per so we will have the output size, so we'll know how many of the kernels we had, and samples contains from the results of MaxPooling for all kernels. For example, basically it should be output size squared and multiplied by kernel count, right? So yeah, that's the same. Yeah, it represents this line. Rows, again, rows we take from the input, and input contains several number of the samples. Okay, taking one. Actually, it's not correct what I wrote here. Okay, let me just write it once again. So basically first, sample rows, and so I have the input data, and that should be inputs. I'm thinking of slice, row, this is the data that contains all outputs from the convolutional array. Maybe actually, I think I will take the row. Then we need to actually subslice it, because we need to get the data for each kernel. So then we have kernel index. We have the kernel data, and it means that we can subslide the input data by kernel I multiplied by input size, and then kernel I plus 1 that should be this, the data. So right now we have then what we can do. And then actually we should do the MaxPooling, right? So we have the inputs and we have the output. So for this kernel output, we should declare so we have the kernel MaxPooling data, and it's going to be float 64. I need to use make. So we have the make float 64, and here we will use output size square. Can I do like this? Actually can. Okay. And right now I think finally I can do something like this. So this is going to be a rectangle of values, and from which one I need to take the data, right? Okay, so for what should be the count layer? I think it should be input size, right? Oh no, we're actually going for the output. Right, so then we should calculate the start I and no start J, right? This is I multiplied by I think it's plus pool size, right? Pool size. And right now I'm thinking maybe I should convert it into matdense, because there is a good reflect this one. It returns the matrix, and with the matrix we can take the dimensions, so we can actually What I'm thinking is how it's easier to implement this logic, because what this starts I and end I defines is the top left, top right, bottom left, bottom right indexes, and then it forms some way of the matrix. And I think it might be easier to iterate it with the matrix. Okay, then kernel. Okay, so it's going to be better. Then I need to take the pulse slice, and that's we can do from the kernel data. We can take the slice, and this is going to be actually start slice. M is the number of the items. Okay. Actually, wait. How? I plus M. Okay. So it's end start J and okay. Then we need to find the max value from this one. Okay, so then we're taking the whole value, which is the max value for the pool size, right? And the last thing we need to do is to write it, right? So let's create in a patch. Well, I mean, this is the output, right? we're actually taking the kernel max pooling data and we're using set. We have G and all value, and that's it. So once we passed over all of the kernel, I mean, this is the data for one of them, but we need to combine, right? Pooling, max pooling out. What will be the size? Do we have the output size, right? Squared. But before we need actually the kernel size, right? Well, the kernel count. Okay, so once we passed over this, it means that the max pooling, we can use the append and we can take the kernel max pooling data. Okay, we add it and then we need to write it into the output. How are we going to do this? We're going to use output set row, and we have the sample I, and then we can use the max pooling output. Okay, let me go over. Okay, so we have the inputs. I'm going to write as many comments as I can. Take the number samples for training or inference, right? Output size, calculate max pooling output size. Can go. So this one we're going over all samples with data that contains all outputs from for current sample. We're allocating the slice to collect all of the max pooling results from all of the kernels. This is why we have the output size and multiplied by the kernel. Then we go in over all kernels separately. For example, here is this one. Okay, so then we take data from specific output from convolution. It's not actually like the right. Specific output or kernel, from my understanding. Yes, we subslicing it by the input size. And then this is the kernel data. And then what we do, we take the kernel max pooling data, the declaring declare max pooling output for kernel for sample. Right, so this is why we have the output size. Then we're going over output size and we need to create a patch. I multiplied by the pool size, J multiplied by the pool size. And we're going over actually iterating over output array. So we need to find a patch window from input data, right? By the pool size, and then okay, and then we have start J and J. Okay, and then we take the maximum value and then we set it to the kernel MaxPooling data. Then we take in the data from it and assign it to MaxPooling output that will contain the results from all of them, and then we set the output, right? I mean, okay, so okay, that looks valid, at least from my perspective. Then what we actually, the interesting part is actually will be to create the backward passes, because right now actually what we have in the convolution in the forward, I think the forward method is done. Yeah, so the backward is empty because I still I wanted to make the MaxPooling first. We have backwards. But instead we have the MaxPooling layer. Okay, so for the backward path, in the MaxPooling, backward path doesn't involve gradient computations, unlike other operations that require gradient calculations, such as convolution fully connected. MaxPooling simply passes the maximum values to the next layer without any further computations. Okay. Therefore, during the backward pass of the MaxPooling, we do not calculate gradients. Instead, we transmit the maximum gradients obtained from the previous layer directly to the corresponding location in the next layer. This process ensures that the maximum gradient values flow through the MaxPooling layer and continue propagating through the network. Basically, it goes in different direction. So it has the number of channels, outputs, I guess that's the same. I think it's the same. The only difference is that but this is the same, right? Okay, so we're basically creating a mask. Okay, now I understand this line. So what it does is actually it creates the patch again, then it gets the maximum value from the patch, and then it generates, so for example, patch is 2x2 matrix, and it will produce 0 for all of the elements that are not equal to the max value, and then it will produce 1 for elements that are equal to the max value. So this is why we get basically we just get in the mask, and then we apply the deal, and then we masking the d values that comes from the next layer, right? Oh, we're taking the value, one value from it, and we multiplying it by the mask, which expands it into the D input and making them bigger. Okay. Okay, so, but the first I need to store the inputs, right? Input data from forwards to be used in backwards. Then what do we, so the inputs, basically the D value that the MaxPooling will have. I think we have the same for the, yeah. Here are the inputs, layer, interface. Yeah, get the inputs. Okay. So we're allocating it here, and that's the same size as the input. Okay, so we can achieve it with the, we can make a copy of the input. Copy. And then what we can do, we can zero them. It's kind of, well, more or less the same. And then we can do, well, actually can copy the previous part. Okay, what is the rows? Rows is the number of the samples. And we can take it even from the D values. Right. Okay, I will need the input data, so that's this one. Okay, but it means that I will need to, I'm still curious how it will work after the fully connected layer. To have the gradients. But what I don't understand is that the MaxPooling will, or should I just connect it to the dense layer? Where's the architecture? Oh, so we, yeah, but how do we connect? I mean, I can create the layer of the size of, well, maybe actually that's the thing. For example, then I will have the, I remember in one of the examples or one of the, I don't remember which one. It's not only the convolution and the pooling, it was also the flatten layer, and the reason, I mean, the need was to, well, I guess convert all of this data. But what I can do here is, for example, I have the 3 MaxPooling results in one array of specific size, and then I can create just a fully a dense layer where every node is connected to one value in the pooling, and I can have like one fully connected layer with 3 multiplied number of the elements 3 multiplied by this number of the number of the outputs multiplied by the number of the size of the pooling, and that will be my fully connected. And in that case, I think it makes it easier to implement, at least right now, because it means that I can just take the whatever data we have from the dense layer. That will be actually the d-values from the dense layer, and then we can just expand them and use next for the convolution, right? But how we can make it? Okay, I will remove for now everything that I don't know I need. Kernel size. Okay, I'm not sure I need this. And this, and this. Okay. So how it will work? We have the kernel data, okay? Then we iterating over, so we have a I haven't drank enough coffee today, apparently. Okay, so we have the patch, right? We already have the patch. So this is the pool size, right? Still needs okay, but I created the D input, right? I have the max, I have the pool value. Oh, but I think what I can do actually right now is okay, the question is how I will access this one actually. So it's going to be in one row, but maybe it's not a big deal. Then we're actually going to have a loop through this, right? So I have 4 wait, RC all right. So what we're going to do, we need to set up, we need to set the value for the D input. So we have the D input, we have set, we have I and J, and then we have the value. The interesting one is actually to build the value, right? Okay, so it's 0, but if value from the patch is no, it's actually wait, not the best code that I wrote, like far away, okay. But if so, we're using ij to no, D input starts I and I'm not sure that this part will be correct in terms of the indexes. J. So the idea that we need to set the input correctly. Oh no, it's not even like this. I need to. This is what I'm doing for the sample, right? So the I will be actually okay. Okay, let me organize it better. I mean, what I need to do is I need to create this part, right? So for the input, I will have I actually already have. For example, wait. So for example, if I want to set something there, I should have the input, for example, set, and for the set, the index will be actually the first one is the sample I, because this is what we do in for the current sample. And then the question is, come on, this one and this one, right? I'm thinking maybe I can calculate it just right now and I don't need to. So for I and j, we can. So I and j will get me this one. So I have the d value, right? I have the d value, which is d values at, and this one is interesting. I guess we'll have the sample I, and again the same. So okay, so basically I need to write a conversion. Well, not a conversion. And I need to write a function that will compute this index, right? For this class. So this is going to use the output width, output height, and okay, that should be a good starting point. Okay, so I need convert Cij into column index for sample data. It should be something like, we have 3 items, so it would be like c multiplied by, wait, it would be something like kernel I multiplied by layer output size squared plus I multiplied by layer output size plus j. Right? So the first one is will offset me with the kernel output. The second one is will offset me over the rows. The last one with the actual value within the row. Okay, so the index is going to be actually this one. Right? Output size. Okay, so this is the index. And then I need to have an internal loop to set the D inputs, right? So this is, but again, this is the start and okay, I guess I need to wait. Oh, that's right. So that should be. So we have the value, and the rest thing is to use expand patch and fill the inputs. So that's going to be my to-do. Right? So basically I need to implement these two things. No, this. Right? I mean, I can. Yeah, I mean, I know. I feel like I confuse myself even more with this one. So probably I can get rid of this one and use one way to access the data from the inputs, because right now what I'm doing, I mean, I'm still going to take the row from the inputs. So I will work with one sample like this one, but when, for example, here it uses the three-dimensional access kernel and the data itself, I will use something like this, but for all of the indexes inside. And instead of having the kernel data, which is the subset of this one, I will just use something like this and convert all of these accesses, like this one, to use this formula and say this one. So that should be, I mean, probably I will create some function that does this conversion for the MaxPooling layer. It will just probably make it easier actually to understand, because right now I have too many temporal arrays and subslicing, and I already feel a little bit lost, and I will have to debug it because there is no way I can do it without any issues and without any errors. So yeah, this is going to be interesting. Okay, but I think right now it's actually, I mean, the main thing I actually understood is how the data will flow, especially how the MaxPooling will be connected to the dense layer. And turns out it's not a big deal. I will actually pass the data as it is right now into the dense layer and let the dense layer figure out what to do with this data. So yes, I will have one MaxPooling result, second MaxPooling result of the third one, and all of them will just flow into the dense layer. It's not that different from the previous implementation when the input for the dense layer was just pixel value, and it was, I think, even weirder. But I think right now it will be okay. I still don't know how I can build convolution on top of the convolution, but one thing at a time. I want to finish with this one first, and then we can, think about the next steps. But for now, I think that's already 1 hour of recording. I don't know how we'll shrink it into the YouTube video, but yeah, to be honest, it goes a little bit slower for various reasons. The first one is unfortunately don't have that much time to record those videos, but I'm trying to record it as much as I can. And the second one is, using the neural networks from Scratchbook was much easier for this stuff because it was very structured and I need to follow. And for example, for the convolutions, it's actually, you cannot find a good, at least for my purposes, a good article that you could follow. Even the one that I'm following right now, I have a question. For example, if you take a look at the convolution itself, I have a big question, where is the convolution? What happened to the biases? They are not used anywhere, or actually they used, okay, we created, yeah, and they're not used in the convolutions anyway. So the one that you can see right now is it's from the dense layer, which I'm using. So this one is already a little bit weird, so probably, and I don't remember right now, I just need to revisit that article. I don't remember how exactly you're adding, I have this one here, yeah, but I'm still not fully understand how exactly you adding it. So is it just added to the overall sum or something else? Because right now, so this is the result, but where is the bias? And I think here it adds bias once you pass the kernel over all three. Where is this one? Okay. Add up all intermediate results. And so we have a kernel for the 3 channels, then we sum it up, and then we add the bias. And I need to check, maybe it's actually available in this article, the question how we're going to implement the backward path in this specific case. But for now, I will actually go without biases, probably, because for the grayscale image, it means that we'll have one channel. There won't be any intermediate results. Well, I can add the bias then, but I don't think it's, well, actually it will be like in a dense layer, but yeah, maybe I will go without the biases, or I will find how to do it properly. But for now, thank you for watching, and I see you in the next video. Bye bye.